5G communication system using Matlab. The outlines of this course are: firstly, an overview of the NOMA communication systems will be presented. Then, the achievable rate offered by the NOMA and orthogonal multiple access techniques. The effect of the imperfect successive interference cancellation on the downlink NOMA rate capacity. The effect of the NOMA fixed power allocation on the bit error rate performance. The number of users that NOMA can support. User pairing in NOMA. The fixed and dynamic power allocation in NOMA. And finally, the estimation of the bit error rate performance and capacity and outage probability of non-orthogonal multiple access communication system over a relay feeding channel. The first outline. In this outline, an overview of the NOMA communication system with respect to orthogonal multiple access will be discussed. Then you will be able to simulate the Shannon capacity formula versus the bandwidth at different values of the signal to noise ratio. The second outline, the achievable rate offered by the NOMA and orthogonal multiple access technique. Using the Matlab codes, you will get the following results. Figure 2.2, the achievable rate bit per second per hertz versus the signal to noise ratio for downlink non-orthogonal multiple access and orthogonal multiple access. The solid line is used for NOMA and dashed lines is used for orthogonal multiple access scheme. Figure 2.3 shows the achievable rate bit per second per hertz versus the signal to noise ratio for uplink NOMA and orthogonal multiple access scheme. Figures 2.2 and 2.3 are simulated using a specific type of fixed power allocation that will be explained through the course content. And the same manner, figures 2.4 and 2.5 show the achievable rate versus the signal to noise ratio for downlink and uplink respectively in case of NOMA with respect to orthogonal multiple access. Also, figures 2.4 and 2.5 for another type of fixed power allocation. In figures 2.2 and 2.3 and 2.4 and 2.5, it is noted that the orthogonal multiple access system outperforms the NOMA system in terms of the achievable rate at low signal to noise ratio. This is due to the NOMA suffers from interference between users at low signal to noise ratio, which will be discussed through the course content. The third outline, the effect of the imperfect successive interference cancellation on the downlink NOMA rate capacity. Using the Matlab, you will get the following result. Figure 3.1 shows the achievable rate bit per second per hertz versus the transmitted power in case of imperfect successive interference cancellation. The imperfect successive interference cancellation is expressed in terms of epsilon. At epsilon equals 0, this is the case of perfect successive interference cancellation, as the epsilon value increased as the achievable rate decreased. The fourth outline, the effect of the NOMA fixed power allocation on the bit error rate performance. Figure 4.1 shows the bit error rate performance versus the fractional power coefficient of the far user at different values of the transmitted power. Figure 4.2 shows the bit error rate performance versus the fractional power coefficient of the near user at different values of the transmitted power. It is clear that the bit error rate performance is varied as the fractional power coefficient of the far or the near user is changing. The fifth outline, the number of users that NOMA can support. An important question is that how many users that NOMA can support. By using detailed steps in Matlab, you will get the following results. Figure 5.1 shows the achievable sum rate versus the number of users of different values of the transmitted power. It is clear that as the number of users increased, as the interference level increased, which results in a degradation in the achievable sum rate capacity. Also, as the amount of the transmitted power increased, as the number of users that can be served increased. As the transmitted power equals 10 dBm, the number of users that can be served is 4, with maximum achievable rate capacity. In the same manner, at transmitted power equals 20 dBm, the maximum achievable rate corresponding to 6 users, and then 8 users, and then 10 users at transmitting power of 14 dBm. Figure 5.2 is the sum rate versus the number of users of non-orthogonal multiple access and orthogonal multiple access systems at different values of the transmitted power. The dashed lines corresponding to orthogonal multiple access system and the solid lines corresponding to non-orthogonal multiple access. Figure 5.3 is the sum rate capacity bit per second per hertz versus the number of users at different values of the fractional power coefficient of the farthest user from 0.6 up to 0.95, and the same manner for figure 5.4. Figure 5.3 corresponding to transmitting power of 20 dBm, and figure 5.4 corresponding to transmitting power of 30 dBm. The sixth outline, the user bearing in nome. According to the previous outline, increasing the number of users may limit the maximum achievable rate to a certain limit due to the interference. One of the methods to solve this problem is the user bearing. In this outline, a simple user bearing based on distance is presented, which are near-far bearing and near-far bearing. Using the Matlab code, you will get the following result. This is the sum rate bit per second per hertz versus the signal to noise ratio for hyperdynamo near-far bearing and hyperdynamo near-far bearing and the single carrier non-orthogonal multiple access system and TDMA. Outline number 7, the fixed and dynamic power allocation in nome. Using the Matlab codes, you will get the following results. This is the sum rate bit per second per hertz versus the transmitted power using fixed and dynamic power allocation. According to the simulation parameters used in the Matlab code, the dynamic power allocation outperforms the fixed power allocation in terms of the sum rate capacity within the variation range of the transmitted power from 0 up to 30 dBm. Figure 7.2 shows the outage probability versus the far user target rate using far and near users for fixed power allocation and far and near user using dynamic or fair power allocation. The outage probability meaning as well as its representation in Matlab are discussed in details through the course content. The final outline, the estimation of the bit error rate performance and capacity and outage probability of non-orthogonal multiple access communication system over a relay feeding channel. Using the Matlab codes, you will get the following result. This is the achievable signal to interference plus noise ratio in decibel versus the transmitted power. The estimation are gamma 1 and gamma 1 2 and gamma 2. Where gamma 1 is the achievable SINR at user 1 and gamma 2 is the achievable SINR at user 2 and gamma 1 2 it is the achievable SINR for decoding the far user signal at the near user. Figure A2 shows the achievable capacity versus the transmitted power of R1 and R12 and R2, where R1 is the achievable capacity of user 1 and R2 is the achievable capacity of user 2 and R12 is the achievable capacity for decoding the far user signal at the near user. Also, gamma 1 and gamma 2 and gamma 1 2 as well as R1, R2, R12 are discussed in details through theoretical explanation and its representation in Matlab in details through the course content. Figure 8.3 shows the outage probability versus the transmitted power of the far and near users. Figure 8.4 shows the bit error rate performance versus the transmitted power of the far and near users. It is clear that the near user outperforms the far user in terms of the outage probability in figure 8.3 and the bit error rate performance in figure 8.4 within the variation range of the transmitted power from 0 up to 40 dBm. This is due to the near user removes the interference caused by the far user via successive interference cancellation process, which discussed in details through the course content. Thank you and see you in the course.